So what I want to speak about during this week is about growth and co-growth in the context of, let's say, hyperbolic geometry. So let me explain a bit what kind of object we're interested in. So imagine you have X, which will be a metric space, and you have a group G, which acts on X, and I will ask that the action is proper and by isometries. If I forget, almost all the action I will talk about will be by isometries. And what I want to do is to sort of measure what is the size of the orbit of G. And in most of cases, when we are interested in, those orbits will be infinite. So the way you can measure something which is infinite is by looking at what's so-called the exponential growth rate. And this is a number which is, well, are denoted by omega of gx, and it can be defined as follows. You take the lim sup as r goes to infinity of 1 over r logarithm of the number of elements that move the point x by at most a distance r. So what does it mean? So basically you look at this set for fixed radius r, you look at how many elements will move a given point by a small distance r. You get a number, or more precisely, you get a function that will depend on r. And since the action is proper, well, this number is always finite. But what you try to understand is what is the asymptotic behavior of this function. Maybe it grows polynomially, maybe it grows exponentially, maybe it grows in between. There are a lot of possible options. And if it grows exponentially, you'd like to measure what the kind of basis of exponential it grows with. And this is how you compute that. So, roughly speaking, very roughly, because you have a lot of errors if you write in this way, but the idea is that balls of radius r, they grow sort of like with, one has to be careful, but something like exponential omega of gx times r. Maybe there are some sub-exponential term in front, something like this, but that's the kind of idea you have to keep in mind. So you can check that this definition will not depend on the point x, it's a triangle inequality. But it does depend on the space you're acting on. If you change the space, even if you take two different calligraphs, you may have different numbers. So let's have some examples of those numbers. So imagine you consider, I'm not gonna like that. Stay here. Okay, so if you take the free abelian group acting on the standard Euclidean space, well, the orbits will grow polynomially, so you get 0 as the exponential growth rate. Another example, which is easy to compute, is you consider the free group with rank r, and you let it act on the calligraph with respect to a free basis. So you have the classical picture. If you take group of rank 2, you get this nice tree. And in this situation, the growth rate will be log of 2r minus 1. try not to break everything. Yep. So less obvious examples. Imagine you consider a surface group, the fundamental group of a surface with genus at least 2. So it acts on the universal cover of the surface, which is the hyperbolic plane, H2. And then you get for this number 1. But as I said, you can vary the space it acts on, and you may get different numbers. So in particular, if you take the same group and you let it act on its Cayley graph, so what I mean, this group, gamma G, has a presentation which is A1, B1, AG, BG, with the product of commutators being 1. And you can look at the Cayley graph here. Well, let me write like this. X will be the Cayley graph with respect to this generating set, A1, B1, A, G, BG. And then you can compute the number at a computation which is due to Canon, if I'm correct. And that will be related to the roots of a certain polynomial. And I need my notes because that's not a nice one. Z to the t to the 4g, 2g plus 1 minus 4g minus 1 z to the 2g plus 4g minus 1 z minus 1. So I'm always confused when you do this kind of computation, but if I'm not mistaken, what you do is you take the absolute value of the smallest absolute value of a root of the polynomial, you take the logarithm, and you get the exponential growth rate. So you'll see you get something which is a pretty different one. When you vary the space, you may vary the number. And there are some other explicit computation which have been done for groups like Boostment Cycle group PS1n for the standard generating set. For lamplighter groups, such things have been done. But in general, let's be honest, computing the exact value of an exponential growth rate, that's a very difficult task. So why do we care if we cannot compute those? Well, the idea is that it's related to other objects coming from geometry, dynamical systems, some combinatorics, and I'll hope to highlight some of them during the discussion. Z to the power of 2g plus 1. That's the one you could not read? My handwriting is so bad. Okay. I'll make some effort. Okay. So, in this series of lecture, I will be more interested in comparing certain growth rates. So maybe explain what I have in mind. So, what have you that? Well, yeah. So I will look at what can be called growth spectra. So fix once for all the group G acting on X. And then you can somehow vary the group, vary the space. So, and look at two different sets. So what I will call the subgroup spectrum, which is, well, all the growth rates of subgroups of G. So if you take any subgroup of G, you let it act in the same space X, and you can compute what is the growth rate of that subgroup. And sometimes we will also look only at the growth rates of normal subgroups, which is a subset of that. And the other spectrum I'm interested in will be the quotient spectrum. So you look at the growth rate of quotient of G acting on the quotient of X. And the goal will be somehow to understand what can we say about those two sets and how the values of growth of subgroups, of growth of quotient, relates to the properties of the group, of the subgroups, quotients, etc. Can we, for instance, describe what is the smallest, the largest value in those sets, those kind of things. And there will be always a standing assumption in everything we do. That will be, we try to understand those sets under the assumption that, let's say X is Gromov hyperbolic. So I will explain everything in this context, but of course you may be interested in those questions also when you have a weaker form of hyperbolicity for your group, but I'll discuss that a bit later. So let me give you a couple of statements that sort of highlight the question I'm interested in, and I'll try to prove some of them along the way to show you how we can use some tools from dynamical systems to answer this question. By the way, just for myself, is everybody familiar with hyperbolicity in the sense of Gromov, or do I need to make some recall? If you need me to do some quick review, let me know. Or is it fine for everyone? Okay. Anyway, if you're too shy to say, just think the tree or the standard hyperbolic space H2, that will be completely enough for everything I say. Okay, so here are kind of some statements I'd like to discuss. So the first one is the following. So, the standing assumption, as I said, that would be, imagine that X now is delta hyperbolic. And for those statements, I will assume for the moment that the group acts properly, co-compactly on X. We can also relax sometimes this assumption. I'll explain when later. And okay, the first statement, which we will start with, is the following. So take H, which is a subgroup of G, which is quasi-convex and infinite index. Then you can wonder what is the growth rate of that subgroup and how big can it be. And the conclusion is it always has to be strictly smaller than the group G. And the first appearance I find of this thing is due to Tammany, Fuder, and Weiss. So that's a first statement I have in mind. Another theorem I'd like to discuss is the following. So now I will look at normal subgroups. So take a normal subgroup which is infinite. And this time I'm wondering how small can the growth rate of this normal subgroup be? And the conclusion here is that the growth rate of this normal subgroup is strictly bigger than 1/2 of the growth rate of G. And I think this is due to Oberlin, mostly. Infinite system, not infinite index. Yeah, well, it's, yeah, well, if you have a normal subgroup in a hyperbolic group, if it's finite in, yeah, well, no, I don't say. Yeah, if it is finite index, you have always equality with the growth rate, regardless whether it's normal or not. If you have finite index, you always have equality. Yes, that's a remark I should have said here. Remark, if you have a finite index subgroup, so when you count how many points you have in the orbits, maybe you missed every one of the 10 points. So if you plug in your computation in the formula above, that multiplicative error will die when taking the logarithm and dividing by r. So that's why if you have a finite index subgroup, that will not change the growth rate of your computing. It's not an infinite, and that's a good remark because it allows me to give you the next statement. So you try to understand, okay, when do you have now equality? What is the largest possible value? And so now take a normal subgroup of G, and the statement is the following, then when do we have equality? Omega nx equals omega gx. Well, this is the two numbers are equals if and only if the quotient G mod n is minimal. So if it, sorry? So I only assume that n is infinite. If n is finite, the growth rate is 0. If n has finite index, the conclusion still holds, obviously. So I'm more interested here in lower bound for the growth rate of n. So I just want it to be sufficiently big, and it turns out that sufficiently big just means infinite. Does that make sense? And so now, if you try to understand what is the, so that somehow gives you a lower bound for the spectrum. Now, if you try to understand what is an upper bound for the spectrum, well, it turns out that we completely understand the equality case here. So if you take a normal subgroup n, the growth rate of n equals the growth rate of g if and only if the quotient is a minimal. So if you are never seen before what an minimal group is, I'll give the definition a bit later. But for the moment, what you can think, keep in mind, is that's sort of a small group, like z squared, or every. No, but anything. For instance, anything that has a growth rate of 0 for the action on the scalar graph will be a minimal. So from my point of view, that's a small group. And the meaning of that statement is if your normal subgroup you are quotienting by is as big as possible, then the quotient has to be small. That's the philosophy of. Yes, you need hyperbolicity for both directions. Because, for instance, you can take G, which is, let's say, a Bohm-like solution group. So in particular, G is the minimal. But it has exponential growth rate, which is positive. Now take for N, the trivial group. The quotient is a minimal, because it's G, but you don't have equality here. So both directions, you need some kind of negative curvature. Well, in this form, well, that's a statement I proved with several co-authors, Dugal, Shapira, and Tapi, but it has a long history. Probably the first occurrences of this statement in particular cases are due to Grigorchuk, Cohen, Brooks, and there is a long list. I'll discuss that a bit later. Okay, so that's the kind of statement we will look at. So, yeah, good remark I forgot also to say. Thank you very much. Don't hesitate to stop me. That's very good. One thing that you can always notice is if you have a subgroup H, as I said, the growth rate is a measurement of the size of the orbit. So you expect a subgroup to be smaller than the big group. Well, if you look at the formula, the cardinality you are computing in that formula, if you take a subgroup, will be smaller than the one for the M. So this is always contained in the interval 0 omega dx. Does that answer your question? So that will allow me again. Can I still use the blackboard on the side, or it's not recommended? Okay. So I need to bring that down. How do I do? Yeah. Up here. Thank you. That's always a German way? I don't know. That's going to be a running joke, I think, for the week. Okay, so you ask me, well, when we vary the group to subgroup, how far can we go in the spectrum? How big can be the growth rate of the subgroup? So we said, okay, we understand, well, it's behind. Yeah, so we understand the equality case when does the growth rate of the subgroup is as big as possible. But there are groups where there are no non-trivial amenable quotients. These may exist. So it means in this theorem above, the only possible subgroup for which you can achieve the largest growth rate would be the group G itself. And you try to understand, you can try to ask when those kind of things happen. And here is another theorem. I'll discuss it if we have time at the very end. Still with the same people. So I make an extra assumption now that I assume that G has Cashdan property. So I don't want to define all the terms as you have seen today. That will be too long. Property T is, let's say, a rigidity property in terms of representation theory. I'll give the definition a bit later, but if you want to have an example in mind, you can take for G a lattice in SPN1. Typically, that would be a good example. If you take a lattice in a higher rank Lie group, you usually get also a group with property T, but this time you don't have the hyperbolicity which is available. So that's why I mentioned this example. And if you're familiar with random groups, that's another source of group with property T. A random group with a large density would be a group with property. And in this situation, we have a sort of a growth gap, meaning that there exists some epsilon positive, such that anytime you pick a subgroup of G, either this subgroup H has finite index, in which case the growth rate of the subgroup is the same as the growth rate of the ambient group, or the growth rate of H is at most the growth rate of G minus epsilon. So if you draw that in line, you have 0, you have the growth rate of G, and there is a gap here. You cannot go inside this part of the spectrum without being equal to omega G, and in which case you have finite. So this generalizes, for instance, some rigidity theorem, which you'd call that for lattices and SPN1. The epsilon will depend on the group G on the space X. Well, everything which is not listed on the blackboard, basically. Yes? No, I don't have such example in mind. I expect something to be true. So what has been recently proved by Samuel Tapie, and I forgot the name of his co-author, sorry, Olivier Glorieux, is that in the amenability criterion, direction G mod n amenable implies equality holds true. You just have to be a bit careful what you define as the growth rate of the group, because if you are in a higher rank situation, this is not completely clear. And I would expect the other direction to be correct. Again, if you are careful about what the definition of the growth rate, but for the moment, I don't think it's proven. Other questions? Okay, so that's the type of statements I am interested in. And actually, more than the statement, what I would like to advocate for is a method that we are going to use. So when you're try to understand growth problems, there are a lot of methods to tackle those questions. And for instance, what you can do is you can try to associate to the elements you try to count a nice representation as a word, let's say, over the generator. By nice, I mean usually you ask that those words are geodesic for the metric you're considering, and with some regularity property, like, well, what you can do when you have a hyperbolic group, you can make sure that this language, the language of all words you're considering is so-called regular, so that you have a lot of tools to tackle them. And then try to do some counting using property of language or other strategies. If you think counting problems also are related to certain dynamical systems, and here the one will be the so-called geodesic flow, and you try to have also coding for understanding the geodesic flow, and then use some properties of stuff shift of finite type, all those kind of things. Here, what I like to do is somehow to stay closer to geometry and understand everything in terms of certain measures on the boundary of the space. And this is what I try to discuss during the mini course. And the reason why I want to do that is many of those statements that I gave you have generalizations outside of the world of hyperbolic group or group acting on hyperbolic space. And usually we have some ad hoc method for each of them. And for me, it's kind of a hint that maybe this theory I want to explain you has some extension beyond hyperbolicity. But this is something which has not been done before. And so I think there is a huge landscape to explore to try to understand how much of what I'm going to tell you today can be generalized in a larger context. So this is why I chose to present I chose this approach using measures on the boundary. Questions so far? Everything is fine? Okay, so let me introduce the main characters that will show up during those lectures. And the character will be conformal measures. So what I'm going to here is, well, okay, let's do this. That's the word I'm going to use. So, in everything I'm going to say, I will assume that the G acts properly on a metric space X. And for simplicity, I'll tell you in a second, I will assume that X is cat minus 1. Everything works in the same way, more or less, if X is hyperbolic, but there are a lot of deltas and some stuff to care about if you are in the general hyperbolic space. So let's take it to be cat minus 1. If you do you know all the definition of cat minus 1? Is there anybody that does not know the definition? That's the right way to ask. So let me give it to you, and if you're afraid of it, just think hyperbolic space H2, that would be perfect. So cat minus 1 space, the idea is to say that you want triangles in the geometry to be thinner than triangles in H2. So if you have your space X, you can draw any triangle with vertex X, Y, Z, and I want to compare this triangle with a triangle in H2. So in H2, I can draw a triangle that would be called a comparison triangle with apices X star, Y star, Z star in such a way that the length of the sides of the triangles are the same on both sides. Okay? And then, well, pick 2 points here, P and Q, and I'll choose comparison point P star and Q star here, making sure that this length here are the same. And then we say that x is cat minus 1 if the distance from P to Q in the space X is at most the distance in H2 from P star to Q star. So the triangle are thinner in X than they are in H2. And I ask that for every triangle X, Y, Z, and for every point PQ on the side of the triangle. But again, if you dislike cat minus 1 space, just think that would be completely enough. X equals H2, or X is a tree. These are two very good examples for everything I'm going to say. Okay? Okay, so the first thing I need to do is to understand a compactification of the space X. So what we want to do is to compactify X. And what we will use to do that is a visual boundary. So, well, I will write it like this. Partial X, that just the space of geodesic rays in X modulo certain equivalence relation, while I say that two rays gamma 1 and gamma 2 are equivalent if the Hausdorff distance is between those two rays is finite. Oh, interesting. And so we can enter this boundary with a topology so that if you add the boundary to the space X, it would be a compact space. So typically, you take the disk model for H2, and the boundary in this situation would just be the unit circle. And the topology, you can get that the usual topology on the unit disk, the closed unit sticks. Sorry? Yeah, let's say X is proper. Yeah. Well, typically, if you ask that the group acts properly concompactly on the space, then X would be automatically proper. Okay, so as I said, I want to have some measures on this boundary. They would be my main characters, and try to understand the action. So yeah, so I forgot to say something. So the action of G on X that will induces an action of G on the compactification, and the action is this one by homomorphism. So the action of the boundary is not by isometries. I have not defined an isometry yet, a metric. This could be done, but I will not do it. And so I will just think of it as an action by a homomorphism. And so, as I said, I want to understand, to relate growth rates of G on X or some supergroup on X to certain properties of measures on this boundary at infinity. So when you do that, the best situation you can expect is, for instance, to have a probability measure on the boundary, which is invariant under the action of the group. And when you have this, you can do a lot of dynamical systems. Unfortunately, this is not something we can expect here. So that's probably a good exercise. So there is, assume that G is non-elementary. I'll give you a definition right after. Then there is no G invariant probability measure on boundary at. So what do I mean by non-elementary? Well, one possible way to define it is, so you have the orbit, let's say I fix a base point O here, and you have the orbits of the group in the space. And I'd like to try to understand how this orbit will accumulate on the boundary at infinity. So we can define a limit set lambda G as the set of accumulation points of an orbit GO in the boundary at infinity. And I will say that the action is non-elementary if this limit set contains at least 3 points. And the nice thing about that is if it contains at least 3 points, that will imply actually that this limit set is infinite, and also that you have some free groups in your subgroup. If you have 0 points in the limit set, that means your orbit is bounded. There's something to prove, but that's the conclusion. And since your action is proper, it means the group is finite. If you have 1 point in the limit set, you have a so-called parabolic action. And if you have 2 points in the limit set, you have a sort of north-south dynamic, and you can prove that your group is virtually cyclic. So these are 3 elementary cases, the 3 first one, and for which you can find an invariant probability measures. But if your group is non-elementary, you will not find such a. So then we'll have to replace those measures by something else. And this is what I want to introduce. These are those conformal densities. Questions? Yeah, oh, sure, yeah. The question is, does this limit set depend on the base point I chose? That's correct? It does not depend on the base point. More or less, that's again the triangle inequality. If you take two different base points, the orbit will be within finite distance, finite Hausdorff distance. So when you degenerate to the boundary, this finite distance is not seen at infinity. So you get the same accumulation. Other questions? I guess if you have two elements, sorry. The question is, this exercise, can you remove the assumption that, so can you remove the hyperbolicity assumption and just assume that you have two elements, some independent elements with a north-south dynamic for each of them? I think so, yeah. Basically, that's the idea. So you give the hint of the proof which is behind. So you have two elements which somehow are independent with different translation axes, and each of them has north-south dynamic, and you see you can push basically everything, all the math somewhere on the boundary, anywhere in the boundary. So that's why there is enough. Other questions? Okay, so I have until 11:15, right? Okay, perfect. Maybe I'll that not the one. Keep that. Where do I need to stop that? Looks good. Okay. So there is one more definition I need to give you before I introduce the densities, the measure we will be interested in. And this is what's called Boostment cycle. So if I fix a point in the boundary at infinity of my group, and I fix a geodesic ray that points to this boundary point. See here, I have a certain geodesic here. Let's say start at my base point O. Then I will define big C of x, y as the following. That will be the limit as t goes to infinity of the distance between x and gamma t minus the distance between y and gamma t. So the limit exists. Just some triangle inequality stuff. And somehow the way we think about it is take 2 points x and y, and somehow I want to measure what is the distance from x to that point at infinity. Well, I cannot directly do that because that's something which is infinite. But what I can compute is whether x is closer to y from the point at infinity. So you look at the point gamma t here on your ray, you compute the difference between those two lengths, and when you pass the limit, you still get something which is finite. And somehow, if this thing is, let's say, negative, that would mean that somehow x is closer to c than the y. That's the idea. And the reason why I assume that the space is ket minus 1 is because we have a very nice feature which is not as smooth in the hyperbolic context. So I can consider in X the following map. which takes a triple of point, x, y, z, and associate the distance from x to z minus the distance from y to z. Everything here is in x. And it turned out that it extends continuously to map this time from x time the compactification of x and the idea is that so if you have x, y, z, you still take the same formula if z is in space x and you have x, y, c, you will associate this Boostment cycle if you're in the boundary. So that's the reason why sometimes I will write that also as bz xy to make everything come. So just comparing distance to a point. The point can be inside the space or on the boundary at infinity. So the fact that, well, first, the fact that this definition I gave you of big C does not depend on the Judith gamma I chose. It uses already the fact that x is ket minus 1, and the continuous extension also uses the fact that x is ket minus 1. If you're working in Gromov hyperbolic space, you have to add some deltas here and there, but the philosophy works more or less in the same way. So as I told you, we cannot find a measure on the boundary of infinity which is invariant under the group action. So what's the best next thing we can do is try to have a measure which is quasi-invariant in the sense that if you push it by an element of the group, it's still absolutely continuous with respect to the original measure. So that's the kind of thing we're going to do, but with some additional data. And this is what I want to introduce now. So that really is the main character for these lectures. So I will say that an S-conformal density is a family mu of measure which are indexed by the point in the space, such that several things. So first, if you look at the total mass of the measure at the base point O, I fix the base point 1 for all. So what I wrote with the double bar here is the total mass. So that's really the integral of the constant function dnu. And I make some normalization assumption. I assume that the total mass of the measure indexed by O is 1. Just to have something which looks like a probability measure. And the second point, that for every x or y in the space, I will assume that nu x is absolutely continuous with respect to nu y. And when you have two measures which are absolutely continuous with respect to one another, you want to compute the Radon-Nikodym derivative. And this is what we are going to try to control. So the Radon-Nikodym derivative at a point C will be exponential minus S to Boostment big C at x, y, c, nu y almost sure. I should have written here there are measures, that's a collection of measures, and that would be convenient, you'll see later, to think of those measures first not on the boundary at infinity, but directly on the whole compactification. So in particular, that point could be a point inside the space, if the measure gives some mass inside. And the next definition, well, the next property you can ask for such a density will say that nu is G invariant if when you push the measure nu x by an element G, you get the measure and nu Gx for every G in G, x and x. So that's a number. That's third. So what is S in this definition? S is a parameter of your measure. That's a number which is assigned to I could have written first, let S be a number, and now I define what is an S conformal density. Does that make sense? And we'll see that this number S does not come, randomly here. This number S will be related to the growth rate of the group. Of course. Well, of course. This is what we're going to see. Almost surely. Yes? So what I mean here is that there are nu x is absolutely continuous to nu y, meaning that every, I never remember in which order I want to say it, every zero measure set for this measure has zero measure for this other measure. Yeah, since I ask it for every point, that's, I don't care. But the correct definition of absolute continuity is the following one. So well, maybe I should recall then, if that's not clear. When you have two measures, nu and mu, two measures, so that nu is absolutely continuous with respect to mu, meaning that every zero measure set for mu is a zero measure set for nu. Then when you have this, you have a theorem which associates a certain function f, which is the random Nicodemus derivative of this ratio. And what does it mean? It means that if phi is a continuous function, the integral of phi against the measure nu is just the integral of phi times f against the measure nu. That's the way to characterize this random Nicodemus derivative. But this thing is, it lives in the function, that's something which is just a measure theoretic construction. So this function is defined mu almost everywhere. At points where mu gives no mass, there it makes no sense to speak about the random Nicodemus derivative. So that's why I wrote nu y almost surely. Does that answer your question? That's fine for everyone? Okay, so that's the kind of measure we are interested in. And as I told you, well, I was thinking of one measure, which is G invariant. I said that's not possible. So we move to, let's have a measure which is quasi-invariant, and I gave you a definition with a collection of measures. So it's just a convenient way for the proofs later, but somehow, if you look at this relation, if you know the measure nu at the base point O, sure. Yeah, so if you give me a second, I'll explain after how we build example of such a thing, and that will make this expression probably more natural. So I was saying, I give you a family of measures, but if you only know the measure at the point O, you know all the measure at all the points because you know the radical derivative. So it's just giving you one measure, but just it's convenient later to have this family of measure for the purposes. And I was thinking about having quasi invariant measure. So a consequence of this definition is that if you push the measure nu by element G, that will be absolutely continuous with respect to nu because that's just a measure at the point GO. And we understand what is the radical derivative because that's just given by the formula by this. So again, I'm working with a family of measures, but at the end of the day, it's just as if I had a single measure. It's just more convenient to correlate the two parts in the definition. Okay, so that's a nice formal definition, but why do such objects exist? And there is a beautiful construction which is due to Sullivan and adjusted after by Peterson to compute such measures, to build such measures. And this is what I try to explain. And that will make clear why we have this Boostment cycle which appears and hopefully make it more natural. In particular, one question which is reasonable to ask is, for which value of S do we have such density? Because you see, if you take, for instance, S equals 0, then this quantity, this identity just tells you that nu x and nu y are just the same. So if you combine with this identity, it means you have an invariant probability measures. So you cannot have a density for S equals 0. Okay, so to build such a measure, what I will look at is the so-called Poincaré series of the group G. So remember, we are interested in counting problems. Usually when you count stuff, you always have, thank you, you always have a counting series. So we will just reformulate in a Dirichlet fashion, but that's exactly the same thing. So the Poincaré series would be the sum of all G of exponential minus S distant from O to GO. It's just a formal series for the moment. And you see that if S is very small, this stuff has a tendency to diverge. And if S is very big, that will converge. And that's just a reformulation of the definition to see that PGS converges if the exponent is larger than omega gx and diverges if S is strictly smaller than this growth rate. Like a power series, you have a radius of convergence. It converges where you're inside, diverges outside. And what's happening exactly at the critical exponent? Well, it depends. And that's why you have a definition that G, or more precisely, the action of G of X is divergent if the Poincare series diverges at a critical exponent, and it would be convergent otherwise. And so once we have this Poincare series, what we can do is the following. So take some number S, which is bigger than the critical exponent, so that the Poincare series converges. And I'm going to look at a certain measure, which has two parameters, S and a point X in the space. And basically what I want to do is to take the sum over all G of exponential minus S, the distance from X to O, times the direct mass at GO. So you have your orbit. And what we try to do basically is try to make sort of a uniform measure on the group. That's very roughly speaking, but imagine you take all the elements at distance R from your base point O. So you take somehow the sphere of radius R in your group. How many elements you have in this sphere? Well, something which is exponential in R. Exponential is the distance here. So if I wanted to take a uniform measure on the sphere of radius R, that will be a sum of exponential minus, well, sum of all the elements on the sphere, exponential minus something times the distance, times the direct at this element. So this kind of idea which is behind. That would be more convenient to get invariance instead of considering sphere of radius R, to really consider all the elements. And so that's why I make this kind of sum here. Does that make sense? But now this is, I want some conformal density, I'd like this to be a probability measure when X equals the origin. Yes? So for the moment, I'm picking S, which is larger than omega G, and then eventually I will let S goes to omega G. Yeah. So as I said, this is probably not a probability measure when X equals O, so just make some rescaling to make sure that it is a probability measure when X equals O. And so that's a measure which is supported on X. Okay? And actually, what you can check is if you take the collection of all those measures, it is a G invariant S conformal density. And it's really, you just rewrite this pure abstract nonsense. You write the definition, and you'll see that all the properties are satisfied. Really, there is nothing deep inside this statement. I wanted to give the details, but I'll be out of time, so maybe I'll do that tomorrow. I'll leave it as an exercise. And as you mentioned, we are more interested to have not S conformal density, but conformal density from S, which is this omega g. So the next step we would like to do is we'll try to understand what's happening for those measures as S approaches that growth rate. But it turns out that the space of probability measures on the compact space is compact. So up to passing to subsequence, you can always make sure that this stuff converges somewhere. So up to passing to a subsequence, this measure nu x s will converge for the weak star topology to certain measure nu x. And what you can check is all the properties I've listed above, they are closed properties. If you have a sequence of measures satisfying any of them, when you pass the limit will still satisfy those properties. So at the limit, what you get is that this measure here, this family is a G invariant S conformal density. Not S now, it's omega G conformal. If there is no ambiguity, I will write omega in subindex G instead of omega G X. That would be more faster. And so this is what it called the Patterson-Sullivan density. So there is just one thing I need to mention. Our goal was to produce a measure on the boundary at infinity. Have we achieved our goal yet or not? Yeah, I'll just finish that and I'll stop. So in general, as I explained to you, it may happen that this measure is not supported on the boundary. But the main fact here is the following. If G is, or if the action of G is divergent, meaning that the Poincaré series diverges at the critical exponent, then this measure we just built is supported on the limit set of the group inside the boundary. Why is that? Well, if you just look at this formula, imagine you try to compute, you have a function f, a continuous function on the space x bar, which is supported outside of the boundary in x. So the support of f, that would be a compact set in x. So it will see only finite many of points in the orbit. So there exists a finite set such that f equals 0 outside the orbit of, well, F restricted and the orbit is 0 outside of its orbit, right? So if you compute now the integral of F with this formula, you see that this will be a finite sum. And how many elements you have in this sum, that does not depend on S. And you rescale by something which has a tendency to explode as S goes to the critical exponent. The ratio will go to 0. Sorry? That a finite subset, the only point in the orbits that my function f will see are the point in the orbit of this finite subset. And outside, I don't see anything. So as I said, this sum will be finite, so you can get a bound which does not depend on S, and you rescale by something which explodes, so at the limit you get 0. So we have done for having a conformal density supported on the boundary. It turns out that if your group is not divergent, you can tweak the construction to still have a measure which is supported on the boundary. I'll not give any detail about it today. And starting from tomorrow, I'll explain you how now we can use those capacitance measures to start getting results about growth and the first statement I gave you at the beginning of the lecture. And I stop here because I'm already out of time.